All right, guys, welcome back. Past couple videos, we kind of introduced again the idea of imaginary numbers, but now we're going to take it one step further towards complex numbers. Complex numbers kind of are just the same thing as imaginary numbers, but well, you're adding a real part. You'll see what I mean when I explain kind of what's written on the slide. So a complex number, a number that can be written in the form a plus bi, where a and b are real numbers. And of course, we know that I is the square root of -1. That never changes. Every complex number has a real part and an imaginary part. So a complex number, it says the form a plus, oops, kind of microphone's in the way, a plus bi. That's what it looks like. It's a complex number. This is really considered one number. But let me give you an example of something that's real instead of using a and b. Let's say, 2 plus 3i. That's a complex number right there. I know it looks like it's, two terms, but really we consider this to be one complex number, where it's got consisting of real part, which is 2, because 2 is like a normal real number, and an imaginary part, which has the imaginary part I in it. So self-explanatory there, but it's a complex number. So 2 plus 3i, that's a complex number. 4 plus 5i, that's a complex number. -1 minus 7i, still a complex number, okay? It's complicated. Complex number. Anyway, moving forward. So find the values of x and y that make the equation true. So we've got an example there, and I'll do that little problem in a second right here, and I'll explain the steps in a moment. But let me kind of clarify what this question's asking, because it's really simple when you think about it. So let's say I've got the complex number 3 plus 7i, right? That's a complex number, right? And it's equal to something plus something I. Well, I wonder what this something must be, and I wonder what that something must be. It's not too tricky. This first part would have to be 3. Second part would have to be 7, because 3 plus 7i would equal 3 plus 7i. So that's really what we're doing here, essentially. To sort of explain the exact same thing one more time, 2 plus 5i equals to, let's say, 2 plus something I. Again, I wonder what that must be. It's probably 5, because it has to be 2 plus 5i equal to 2 plus 5i. That's all we're essentially doing in these problems. So look at this equation, or this complicated complex number. All right, so we have a real part of each of these complex numbers, and we have, wait for it, different colors, imaginary parts of complex numbers. So wait for it, there we go. We're gonna say, okay, 3x has to be the same thing as 6, right? Because again, something plus something I has to equal something plus something I. So the real parts have to be the same. So 3x would have to be the same thing as 6. So we're gonna have to figure out what makes not 3x plus 6. What makes 3x the same thing as 6? And the imaginary parts also have to equal. Whatever's here has to be the same thing as whatever's here. So in this case, we have -5. You've got to pay close attention to that negative sometimes. -5 equal to -10y. All right? Those pieces have to match. So for the first part in red, wait for it, there we go. X must, if you want to solve it, you can solve it, divide by 3. But x has to be 2. If x is 2, then this equals 6, which will be the same thing as 6, of course. So, and now to find out what y has to be, again, this is probably a little more easier if you solve. We have to divide by -10, so it's going to be a fraction, but that's okay. This is going to be a positive 1/2 equal to y. Y would have to equal 1/2. All right, so it's equate the real parts. So that's what I did here in red. So I put the real parts together. I'm going to circle it in blue, trigger you guys. Oh, wait. To get this is going to be even better. All right, equate the imaginary parts. I'm going to circle those in blue and red. Oh, I'm so sorry. But set them equal to each other, solve for the variable, and that's essentially it. It's not really a complicated process, or is it? Because it's complex numbers. Oh, man, you see what I did there? All right. Well, we didn't do enough examples of that. So let me, before I get to complex conjugates, I'm going to use this slide as a template, okay? Because I want to do just a couple more. I'm going to make some up. Let's say I've got, that's a beautiful number, 5 plus 14, no. Let's make, yeah, wait for it. Let's, okay. 2yi, okay, equals to, x plus 14i. So I have to figure out what is x, and I have to figure out what is y. So x, that's my real part. That real part has to be the same as this real part. So x has to be equal to 5. And I would solve that if I had an equation, but that is the answer. X would have to be 5. Now let's focus on the y part. Now, I've got 2yi here, and I've got 14i here. Now, you don't have to really worry about the I. I don't think I explained that the first time I did an example. You don't have to worry about the I, okay? If 2y is the same as 14, then, I mean, they both already have I in it, so you don't, like I said, you don't have to worry about them because the I is already there for both of them. But 2y has to be the same thing as 14. So 2y equals 14. Divided by 2, we'll figure out, hey, you know what? Y is 7. If y is 7, then those two parts are equal to each other. So not too much of a handful. Let's do just one more, just for good practice. Let's use purple or something this time. Let's say I've got 3x. No, wait. Let's do something harder. Okay. 4x. Yes. All right. Plus 27i. Ooh, fancy. Equals 12 minus, tricky. Let me put this in parentheses for just the time being. Minus 9. Ooh, that's not a 9. That's a 9. 9yi. All right, so again, real parts have to be real parts. So 4x has to be the same as 12. So 4x has to be the same as 12, which if you solve for x means x is equal to 3. Piece of cake. Why do you do that? I don't know. All right, and then let's use green. Let's just, go off the handle here, okay? 27 has to be the same. Now, wait for it. Negative 9y. I know this was positive 27. I didn't really take that into consideration, but when I say 27, it's kind of implied that it's positive 27. So 27 has to be the same as negative. That's why you got to pay close attention to those minus signs sometimes. Negative 9y. And so for that to be 27, divide by negative 9, you get negative 3 is our y value. All right, moving on. Complex conjugates. Complex conjugates, also pretty simple simple process. The general rule of thumb is stated right here, complex conjugates. Real parts are equal. So keep that in mind. Real parts are equal, which means real parts do not change. And imaginary parts are opposites, which means they do change. So, give you an example. All right. Let's say I have a complex number that's 5 plus 4i. Its complex conjugate is 5 minus 4i. So you see what I did there? Real parts. Real parts are equal. Now notice 5 is the real part. It's the same. It didn't change. This is my conjugate here at the bottom, right? 5 is my real part. It stays the same. I'm not changing it to a negative 5. I keep 5 like normal, right? But what do I change? I change. No, wait for it. Okay. Imaginary parts are opposites. So see what I did? The imaginary part, I changed the sign from a plus to a minus. There you go, complex conjugate. So it's really that simple. We're not really doing any math here. We're just sort of identifying its opposite. It's kind of like saying, what's the opposite of negative 2? And you would say positive 2. That's really all we're doing with these problems. So let's try another, shall we? 7 minus 3i. Its complex conjugate is 7 plus 3i. Fancy, I know. Real part, again, did not change. Positive 7, still positive 7. Imaginary part, though, did change from a negative 3 to a positive 3. There you go. It's that was it. Now, sometimes they can throw little curveballs at you, though, so this is why, you may be thinking it's easy. It is easy, but don't get fumbled up by this, okay? What if it's 3i plus... Think of it. Give me a number. Guys, shout a number out to your computer screen. Let me hear it, okay? 3i plus what should be my real part? Okay, 11. Good job. That's what I heard. I heard you say 11. All right. So, complex conjugate. Do not say the complex conjugate is 3i minus 11. That's a no-no. See? Because the real part is 11 here. You're not supposed to change that. The real parts are supposed to be the same. Okay? What should change is the imaginary parts. So the positive 3i should become a negative 3i. The 11 should not change. So your complex conjugate is this. You change the sign on the imaginary part, and you leave the sign alone on the real part. All right? So don't get fumbled up. People will get those mixed up all the time. What I just encourage you to do is get in the habit of just writing, what was it? What was that thing that I just had before? Was it positive 3i plus 11? What I encourage you to do is to swap these around, and then do the problem. So typically we write the real part first and the real part first and the imaginary part second. So, the real part's 11, imaginary part's 3i. So really, if I want it kind of in a quote-unquote standard form, I should write this as 11 plus 3i. And then the complex conjugate is kind of as your normal way of thinking. You change that sign, right, to 11 minus 3i. Same thing as my last answer, but this is a little bit more of standard practice where you write the complex number the way it's supposed to be written, because here it's not written the way it's supposed to be written, because you're supposed to have the real part first, the imaginary part second, kind of standard practice. All right, so whoa, okay, slow down. Anyway, that's your complex conjugate right there. Let's see what else this thing has to say. If quadratic with a non-real root with complex conjugates, great. Find these complex conjugate. Write a plus bi. Find a minus bi. Simplify. Okay, piece of cake. So we'll do a couple here. So real part is 8. Imaginary numbers 5i. So we keep the real part the same. We make the imaginary part the opposite. So there you go. There's your complex number there. I'm going to make this a colorful slide. So 6i. Notice there is no real part. So the real part still doesn't change. But the imaginary part is 6i, which we do change. So the complex conjugate is just negative 6i. Piece of cake. We have 20 is 9 minus I. Let me get another color. What color should I use, guys? What color should I use? If you said yellow, shame on you. I'm going to use green. 9 minus I. So the real part is 9. We keep that the same. The imaginary part's negative I. So we're going to change that to positive I. Call it a day. And 21, this gets a lot of people, so be careful. Again, give me color. Give me color that I haven't used. I heard you say purple. Shame on you. I'm going to use blue, light blue, okay? So notice the imaginary part's written first and the real part's written second. Do not say the complex conjugate is I minus square root of 3 because you would be wrong, okay? What I would do first is I would just go ahead and reverse these. So let's write the real part, which is square root of 3 first, and then plus I. That's the way it's supposed to be written, but its complex conjugate would be square root of 3 minus I. So this would be the complex conjugate. You could have just also said, conjugate is just changing this to a negative I, leaving the real part the same. These two answers are the exact same thing. However, the one on the right here, okay, is more of your standard practice, kind of the answer you should probably write on your paper anyway, normally, okay, and that's it. Okay, moving on. All right, how long is this video? Hold on. Should I stop this here? I'm gonna do this graphing part, and then I'll stop after the graphing part. So graphing complex numbers, it's pretty simple. Yeah, so you know your coordinate plane, how it normally is. Let me use black here because black's a boring color and coordinate planes are boring. All right, coordinate plane, you have an x-axis and a y-axis, right? So if you have the point 2, 4, you have x 2, y is 4. So you go 1, 2, y, and then 4, and then you'd have the point. It's pretty much the same thing when you're graphing complex numbers, except you're not going to have an x-axis and a y-axis. You're going to have a real number axis and an imaginary number axis. But it looks the same, it acts the same, it's not really any different. So if you have a complex number, let's give an example that's like 2 minus I. Well, the real number here is positive 2, so on the real axis you would go over to positive 2, right, which is there. And then the imaginary part is negative 1i, because negative I is negative 1i. So you would go down to negative 1 on the imaginary axis, so you'd go over 2 and down negative 1, and you would have that point right there. That would be the point 2 minus I on our graph. So it's kind of like graphing any normal order pair, but it looks funnier, and for some reason that's interesting to us. Okay, so let's graph a few of these. Okay, let's again use color. So what should be the first color? Good, red was the choice I was going to pick as well. So A, 2 minus 3i. So the real part is 2, so you go to 2 on the real axis. And then the imaginary part's negative 3, so you go down negative 3 on the imaginary axis, and you'd have a point right there. See, that is 2 on the real axis and negative 3 on the imaginary axis. There you go. All right, what color should I use next? Good, green is what I was going to select anyway. Negative 1 plus 4i. So negative 1 is the real number, so on the real axis you go to negative 1. And then 4, positive 4, is the imaginary axis. So negative 1 and then plus 4i. So right there. That would be point B. What color should I use next? Good, purple, blue, I meant, is what I was going to say. Dark blue. Anyway, 4 plus I. 4 is the real part. So 4 on the real axis, and then plus 1 on the imaginary axis. So that would be right here. And then what's one more color? Let's go ahead and use yellow for you weird people. Negative I. So there's no real number here, so I'm not going anywhere on the real axis. I'm just going to go down 1 on the imaginary axis, and I'm going to put that point right there. Hopefully you can see it. If you don't, blame the people that wanted to use yellow. And that's graphing complex numbers, basically. And you can see those points show up where I drew them. All right, next video we'll talk about whatever this is. See you then. Have a good day.